Here's the situation. A horse pulls a cart with a force of 400 newtons. However, according to Newton's third law, whenever the horse pulls the cart, there is an equal and opposite reaction of the cart pulling the horse. Therefore, the cart pulls the horse with a force of negative 400 newtons. So here's the problem. How does the cart move? Shouldn't these two forces cancel each other out, giving a net force of 0? So here's the situation. We've got the cart pulled forward by the horse. So there's an applied force from the horse, and it's a value of 400 newtons. And the horse has an applied force from the cart in the opposite direction of negative 400 newtons. So the question is, why don't these cancel out? So explain why the force of the horse on the cart is not canceled by the reaction force of the cart on the horse. Use the diagram above and any other math or drawings to help you explain your answer. Hint, label forces on both the horse and the cart. So a good starting point is to draw all the forces. What are all the forces acting on the cart? What are all the forces acting on the horse? See if you can figure out what's going on here. Why aren't these forces canceling? Because they're equal and opposite. One's 400, one's negative 400. Why don't they cancel? Here's the other thing that's going to help. I want you to flip over to the back page. I want you to read this page here. There's several diagrams. Read the pictures too. They're really helpful for understanding this. I want you to try to understand what's going on with this system. So, an interesting question often arises. Since action and reaction forces are equal and opposite, why don't they cancel to 0? To answer this question, we must consider the system involved. So read about systems, figure out what systems are, see if you can apply that to the horse and cart to figure out why these forces don't cancel. Because they can't cancel or the horse will never move. Or if they do cancel, there must be something else going on. Okay? So see if you can figure out what are the forces acting on the horse and the cart. Apply this idea of systems and see if you can figure out what's going on. Okay? It talks about internal and external forces. Internal forces occur inside of a system. External forces occur outside of a system. So if we're talking about the system being the horse and the cart, what type of forces are these? Internal or external? They're internal forces. They're inside the system. The system is the horse and the cart. And what effect do internal forces have? None. They have no effect. So the first and easiest explanation for why don't these forces cancel out is because they don't matter for the overall motion. Okay? You are going to see they do matter, but they're not going to affect the overall motion because they're internal forces. So these are internal forces. Here's an example of internal forces. A little while ago, I took my kids to the zoo. And what my kids decided to do, they didn't want to go home. So what they decided they were going to do is they were going to push backwards on the car from their car seats. So they're in their car seats pushing backwards on the car while I'm driving forward. And they're screaming in the back seat, "Why are we going forwards? We're pushing backwards." And I get it, right? Like every action has an equal and opposite reaction. So if I'm going forward and you apply a backward force that's against my motion, you would think that would cancel out. But it's an internal force. They're pushing forward. I am driving forwards. They're pushing back. Those forces are internal. They don't have an effect on the overall motion. What affects the overall motion? The tires on the road. That's an external force. And so that's what's affecting the overall motion. That's not what's affecting the internal thing. So that's internal versus external forces. But let's look a little bit differently. Let's look just at the cart. What are the forces on the cart? So obviously, the applied force from the horse is on the cart. Normal force is on the cart. Gravity is on the cart. What other force is on the cart? A lot of you mentioned this one. Easton?
Force of
Friction. Okay. So these forces are equal and opposite. But they're equal and opposite because of Newton's second law. The net force up and down is zero. That's why those are equal and opposite. Does the applied force in friction have to be equal and opposite? No, they don't. They don't have to be equal and opposite. So, if friction is small, which it will be with tires, with wheels, what will happen to the cart? It'll accelerate forward because we're worried about the system just being the cart. So the cart will accelerate forwards because of the applied force from the horse. Okay, that makes sense. But what about the horse? Isn't the horse pulled backwards by 400? So why is the horse going forward? Normal force, gravity, applied force from the cart. Why is the horse going forward? I'm missing one force. What is the force I'm missing? You're right. What am I missing? Why does the horse go forward? Stick with it, Easton. No, good guess though. Well, I shouldn't say that. It is friction, but not in the way you're thinking. Applied force from what? From its legs or from the ground or whatever you want to call it, but there's an applied force forward. Does that applied force have to equal the 400? No. So what are the external forces? The external forces are the applied force from the horse's legs and the friction force of the cart. As long as those are not equal and opposite, it'll move. So are these equal and opposite? Yes. Do they cancel out? Kind of, but not really, because they're acting on two separate objects. One acts on the cart, the other acts on the horse. And those forces did not cancel out. Okay? All right, good job today, y'all. If you're not done with the lab, get that lab finished.